Okay, so today I'm just going to cover the sort of the elementary feedback theory, and this is kind of essential trying to connect with the two-stage op-amp design, because we'll be talking a lot about compensating the op-amp, and the compensation is all to do with feedback. So I'll try to cover sort of a little bit on the motivation, a little bit on the historical perspective, and why we use the feedback amplifier, which is kind of ubiquitous nowadays, or it's been since 1927. Black's feedback amplifier, which is being used. So that's what I'll try to cover. But first, I'll just quickly go to the differential amplifier, which I think covered before I left 2 weeks ago. And this is kind of related to the motivation behind the feedback amplifier, which I'll talk a little about, mostly the gain sensitivity and distortion. So I'll just quickly recap so that you guys remember, what a differential amplifier looks like, and two of its most important function. So the first thing we had said that for a differential amplifier, the common mode gain needs to be 0. In other words, like, here I had shown the drain current flowing through these two transistors here. So the ID1, ID2 is shown over here as a function of the common mode voltage. Let me just draw this down here. Common mode voltage, which is defined as the two input voltage divided by 2. Essentially, the two node voltages here, V plus and V minus, when they move together, you don't want the current to change because of reasons I had explained, noise immunity and so on. So that's one of the functions. So you can see as the VICM is increasing, both the current remain fixed. So that's the common. So that's basically, we had defined the common mode gain, let's say, as ACM. You want that to be as close to 0, right? And I just showed the large signal current through the two MOS transistor. As you can see, that the two currents flowing through M1 and M2 are complementary in nature. So as VIP is increasing with respect to VIM, the current in Q1 will increase, which is ID1 here, right here, and equivalently the current in Q2 will decrease, because this I bias is always equal to ID1 plus ID2, right? That's just KCL at this node. So if you do KCL at this node, this should satisfy. So if that has to satisfy, then the current will flow in this complementary manner. And if you take the difference of the current, then that's how it should look like. So that's the current, and you usually drop this across a load to create some V out if you want to. So this ID2 minus ID1 minus ID1, you'll drop it across some load resistance RL, or the output impedance of the transistors, like we saw with the differential amplifier. Now, one thing I want to point out is, I won't go into the equation here, but when we did the small signal, we assumed that it is in this linear region. But as we go away, so in other words, as these two input are increasing differentially, so VID is increasing, you'll start getting into this non-linear region. This is not linear anymore, right? So if your signal is really large, then you're going to distort. So this is the distortion region. And that's one of the reasons we'll be using feedback amplifier. And I'll cover that too, like how feedback helps with that distortion. So this is a simple differential amplifier, which we showed that V out over V in, small signal, again, is either GM1 or GM2, there's the same value, times the output impedance here, this R out, right? And the R out is nothing but, in this case, the output impedance of that's 4 RDS4 in parallel with RDS2, right? So Now, this is another reason we use feedback a lot of times, is because let's say if I tell you that I want a gain. So for example, most of the time you're designing amplifier because we want a certain gain, right? So let's say, for example, you're designing an audio amplifier. I give you this amplifier, certain A1, and you say, okay, I want to put in V in, and I want the output V out to be as close to A1, and sometimes it needs to be exactly the same. Otherwise, you won't meet your specification for whatever that application is. So you really want that. So you can say, oh, I'll just make this equal to A1, and then I can just use this amplifier for whatever I want. In IC design, one of the main problems with this is both GM as well as RDS, these two quantities vary dramatically. I mean, they will vary plus minus 50% over from chip to chip, which is usually called process. So this is usually called the process corners, and then temperature as well, as the temperature changes. And typically the temperature range for consumer parts are minus 20 degree C to 85 degrees C. So for example, all the chips you have in your cell phones, which you're holding in your hand, they are actually spec'd at this. In other words, your cell phone, every chip inside your cell phone has to function for this temperature. Now you might ask, I never live in a place which is 85 degrees centigrade. That's the junction temperature. So let's say you have a hot summer where it is 40 degrees C, then you can have another 45 degrees C temperature within the junction, because what's called the temperature resistance inside a chip. For industrial parts, it's actually minus 40. Industrial or automotive parts is actually 125 degrees C. So minus 40 to 125. So these are really large temperature variations, and this will vary a lot over the temperature. So you can't keep a gain constant over process or temperature. So that's sort of the genesis of the feedback, which I'll show how, what was the origin of it. Just before that, I briefly touched upon the distortion. So I'll quickly show why we get distortion, from the amplifiers we're dealing with. Now, I won't go show the differential amplifier one. It's a little bit involved, but I'll give you material, but I'll show you with a common source amplifier. So let's say you had a common source amplifier, which I think by now everyone is familiar with. So, if I give us some signal with a voltage bias, so let's say this voltage, and that's your output, and that's your, this is some load RL, that's your output V out. This is your small signal VI, and this is some bias voltage V to set your DC bias. So you have some DC current flowing through IB. So you set VB such that you have a DC current IB, right? And this is some transistor M1, right? Now the gain you wrote when you did your small signal is V out over VI. You just wrote GM1 times RDS 1 parallel with RL, right? That's your, yeah. But that was assuming that the signal is really small. But let's say you did not have that assumption, because my signal could vary anything. So let's assume VI is some, and here I'm just giving you one tone, for example. This is just one tone, and this could be just, let's say, a C sharp on your piano or whatever it is, right? Just one tone, VM sine omega t. If that's the case, and now let's say I want to write the entire expression, I can write V out, but the only thing which is nonlinear is actually the drain current here, IDS1, let's say, and assuming that even though the signal is large, this assumption is that you're still in saturation. It may not be, but I'm making that assumption, in which most of the cases it is, right? So if that is in saturation or an active region, then that's your equation, right? Which is VGS minus the threshold voltage square. And obviously here I'm neglecting lambda, but that's not important. Let's say the lambda is pretty high. And this I can write as mu n Cox over 2 W over L, and VGS in this case is some DC bias VB plus your, let's say, your audio signal here, sine omega t minus VTH whole square, right? So if I take this term over here and expand it from this square term, what you're going to get is you're going to get IB. I'm not going to write that, but just trust me that you're going to get IB. And that's because if I make this 0, Vm sine omega 0, then VB minus VTH whole square, that's nothing but IB, right? So that's where IB comes from. Now, you'll get, because it's a square relation, you'll get the linear term. And again, I'm just going to write the result. Just trust me on that one. W over L VB minus VTH times Vm sine omega t. And then you're also going to get the square term, because there is a square term inside that. Again, if I put all the terms together, you're going to get something like this. And you'll get a sine square term, and I can just expand that to a cosine term, sine omega t. And this will again be a DC term, which will add on to this, because there is a DC term on your square relationship, okay? So this is a complete term actually, so it's not linearized, but you can see here, so that's your DC term, which, let's say you didn't have any audio signal in it, you would just get this IB flowing through the transistor, and V out will be just IB times RL. Now, once you give a signal, you get this linear term, and if you recognize this term, this is nothing actually what you calculated GM as. So this is 2IB. If you just take the algebra and reshuffle it, you'll see that this is 2IB over V effective, and V effective is this term here, if you remember, right? And then the linear term. So whatever tone you're giving in, like as I said, let's say you're giving in a C sharp of a piano, you want that same C sharp of the piano here. So that's the term you're getting. But here you get some other omega. So let's say C sharp was, I don't know what C sharp is, but let's say 5 kilohertz. Here you're going to get 10 kilohertz, and that's your distortion. So you probably, heard it a lot of times in your mostly audio amplifiers, even on your phones. If it is distorting, you'll hear a crackling sound or some sound like that, and that's because of this term here. So you get this distortion term here, right? So your output actually has, some K times V in term, but it also has this distortion, let's say, I'll just write it as VD term, and which is unwanted. And we'll see how we can eliminate that using feedback, okay? Okay, so just a little bit of a historical perspective. So the feedback, before feedback, people were actually trying to build amplifiers in open loop, right? Just like what I showed. If you just give a common source amplifier and I give you a gain of some A1, let's say 100, you try to get GM R1. But obviously the IC design is a very recent phenomenon. When I say recent, it's probably a couple of decades. Feedback has been there. This feedback has been there since 1927. So at that time, what people were trying to do was lay out transatlantic phone lines. So they were just trying to have some gain A1, across the Atlantic actually. But it was very difficult for them to control this. So they were getting a lot of distortion, like as I said, and this was varying a lot, and they wanted that gain to be constant. So initially, actually, they tried feed-forward technique to cancel distortion and equalize gain. and that was very difficult to match. So they weren't able to do. So the feedback, the technique we use pretty much, all amplifier design or any feedback design is what's called the Black's feedback design. It comes from an engineer named Harold Black, who used to work for AT&T Bell Labs. And when he was trying to solve the same problem for AT&T phone lines in 1927, he came back with the feedback principle. So the principle is, obviously you've seen all, but if you look at the genesis of it, so they were trying to have a block here, right? And this block, they had some V in they were trying to provide, and let's say you wanted a gain G, they wanted G times V in as your V out, right? Now, obviously they were having problem, like as I said, just constructing an amplifier open loop. So what Black came up with is, okay, let's assume that this is G times V in, and I'm having problems settling this. And let's say somehow I settle this value to G in, and he said, okay, what if I take a portion of it, I'll take a portion of it, and let's call that portion beta. And this beta, you make it equal to, this beta, you make it equal to 1 over G. The gain you wanted, you make the inverse of that. So it's actually attenuator. So let's say you wanted a 10 times gain. So you get 10 times V here, this is 0.1. So what you get here actually is V in, right? You get V in here. And so what his idea was that, okay, now I take a summer block, so that's your V in, and then I take this feedback and subtract it. The reason you subtract it is because you get this, so obviously if this was exactly V in, this will be 0, right? But his idea was that I want G times V in here. What if I put a really large gain here? So let's call that A naught, okay? And if that's a really large A naught, then I need a really small signal here. Let's call that error E to give me this G times V in. So this feedbacks make sure that this is equal to 1 over G, which means that this will force to G times V in. And if this is varying a lot, then I just need a very small error amplifier. I mean, small error. Now, in order to get a small error, this needs to vary, the output needs to vary by a very small amount. So you can vary this a lot, but not vary the output a lot. So, and that was the basic principle of it. So if you write the equation, and we'll show that right now why that happens, but that was kind of his intuitive thought, and from that he got that. So if you write V out over V in, now you take from output input with this entire feedback, you write the algebra for it, you're going to get this expression, basically 1 plus beta times A naught, right? So, and this is what we call it as the closed loop transfer function. So the A naught is this open loop transfer function of this amplifier, and we put this attenuator, put it in a feedback and negative feedback, and we call this the closed loop transfer function. And now this closed loop transfer function, we want this whatever desired gain, G times, desired, that's what we want here, all right? Okay, so how does this solve our problem? So, so this term here, this beta times A naught, is a lot of times you'll see will be called as the loop gain, or simply L, or the transmission T, or the transmission factor. And that's a critical one, and we'll see when we're doing op-amp compensation how we are using that. The reason it's called loop gain is, let's say you make this equal to 0 and you break the loop here, and if you put an input here, you go around the loop, come back here, that gain is nothing but A naught times beta, right? So that's why it's called the loop gain or L. So that's just, so every time you see loop gain, that's what it means. It's basically the gain around the whole loop with V in equals to 0. That's what it means. All independent sources inside 0. Okay, so let's first talk about gain sensitivity. So we said, like for example, the common source amplifier, which I showed you, we said the gain varies a lot, right? And I don't want my amplifier gain to vary. I want it to be constant. So with this closed loop, let's see what the gain sensitivity is. So what I really want to find out is the closed loop sensitivity for the open loop gain, right? So let me draw the feedback here for your reference again. So that's your open loop gain. And then I put feedback factor, subtract it. So this is minus, that's plus here, V in, V out. And we said the closed loop transfer function is A0 over 1 plus beta times A0, right? So we said, okay, we don't have control on this amplifier, but oh, maybe what I should mention is, so you might ask me, well, we don't have control over this one, but we are saying that we need an accurate beta, right? So how do we get that? Now, like as I said, the beta is usually 1 over G, which is actually attenuator. And it's very easy to get attenuator. You just take a resistor divider, for example. That's your attenuator right there, right? So some V in here and that V out here, and you get attenuator, right? So it's that's very easy to get and very accurate to get. And the resistor variation or the ratio of resistor variation, even in a chip, you can get it to within 0.1%. That's very accurate. And that's why we can use this technique here, right? Okay, so I'll just show you the direct result of it. So basically what we want to see is that what is the sensitivity as A naught is varying for the closed loop transfer function. And like I said, the closed loop transfer function is 1 times beta times A naught. And if you solve the entire thing, you're going to get 1 plus beta times A naught whole square. So you can see that if this term is really large, then your sensitivity, the change of the closed loop gain to open loop gain is very small. So let me define the I think more sensible definition of sensitivity is what is the change of the percentage of your closed loop gain when there is a certain percentage of A naught, right? So let's say you change this by 10%, how much is this going to be changed? So that's a maybe a better definition of sensitivity. And here again, you substitute the closed loop transfer function, and this is just A naught. If you do that, you'll actually get 1 over 1 plus beta times A naught, which is, you can write it as 1 plus the loop gain or 1 plus the transmission gain. It's all the same, right? So if your beta times A naught is larger than 1, which means that I have a really large A naught, then the sensitivity is really, really small, right? Which means that I can change the sensitivity. I can change the gain of the open loop transfer function, and it will not change the gain of the closed loop by that much. So for example, in this case, let's take an example. So let's say you wanted a closed loop gain, ACL closed loop gain of 10, which means that you want to set the beta to be 1 over 10, right? And let's choose the open loop transfer function or the open loop gain to be about 1000, which is typical. And if in dB, this is about 60 dB. So this is also typical. So let's say these are the numbers. So based on this, the sensitivity here is 1 over 1 plus 1000 over 10. So that's 100, right? So this is roughly equal to 0.01, correct? So what it means is that let's say if I change A naught by 10%, so for example, I had 1000 of gain, I changed it to 900, 900, then my ACL will only change by 0.01 times 10%, which is 0.1%, right? Which means that it's 1 in 1,000 part, basically, change, which is really small. And that's exactly what we want. So I'll show that with an example too. So everyone is familiar with op-amp circuits. So you take an op-amp and let's say you wanted a gain of 10, let's say, and this is an inverting amplifier. So let's say this is your VI, that's your V out, and you ground this. So that's, let's say, a feedback resistor. That's your input resistor feedback. So if you want V0 over VI, and this is a inverting amplifier, so I'll say minus 10. If you want, excuse me, minus 10, then you want RF over RI to be 10, right? And if you see over here, you'll see that that RF over RI is nothing your beta structure, right? That's your feedback structure. So that's RF, that's RI, and this is your V out, and that's your ground. So this is your feedback structure, and you can see that the beta is 1 over 10 here, right? So that's really the same feedback you've been doing for your op-amp. That's nothing but your 1927's Black's feedback formula. And let's assume that this op-amp has a gain of 1,000, like as we said last time. Now, if you write the closed loop transfer function, that's A naught over 1 plus beta times A naught. And in this case, it'll be 1,000 over 101, which is roughly 9.90099, right? This is, I've calculated, just trust me with that. Now let's say the open loop gain changed from, went from 1,000, and like we said 10%, let's say went 10% lower, so which means that it went to 900. So that's your new gain. So what's your closed loop transfer function now? So it'll be 900 by 900, sorry, 91, 1 plus beta times A naught, so that'll be 91. And if you calculate it exactly to the 4th decimal place, it's 9.8901, right? So the percentage error, if you see, it's 9.90099 minus 9.8901 over, let's say, you just take the 9.0099. That's roughly about 0.1%, which was predicted in your our last equation, right? So you change this by 10%, which is huge. Your closed loop transfer function almost remains constant. It doesn't change, right? So that's one problem solved. We said the two major problems we had was distortion and gain sensitivity. So by putting a large gain, putting this feedback with attenuator, we can actually have a pretty constant gain, right? So let's look at distortion now. So for the distortion, like as I showed earlier, you can model, it was a nonlinear transfer function, but I can actually linearize the model by saying, okay, I have some amplifier, I wanted a gain of A1, but not just did I get A1, but I got this term VD along with that, right? So that's your V in, that's your V out. And so you get V out equals to A1 times V in plus this distortion term, and which we calculated for a simple common source amplifier to be a constant terms times the cos 2 omega t, and that's this term, and that's undesirable. I don't want, I just want this, right? And we said obviously this is also varying a lot. Now if I take this same amplifier and put it in feedback, but I put a large gain before that, so what I'm going to do is I'm going to put a large gain, I'll call this A0. I'll put that same amplifier, this amplifier here. And if I have the same amplifier, same output, then I'm going to get the same distortion as well. So I'll add that distortion term, right? And that's your V out. But obviously this is now the gain is too high, and I can apply the same Black's feedback principle, put this attenuator here, and then sum it or subtract it here, and that's your V in and that's your V out, right? So let's see if this does what we want to. Now, if I just calculate, so let's say VD equals to 0. So we can do superposition because this is a linear model now. So we took a nonlinear model. We say, okay, in a nonlinear model, we get this linear term and we get this nonlinear term. And I said, I'm going to do a linear analysis of that by knowing a priori that this distortion is created, right? So this is a linear model now. Now, if this is a linear model, I can use superposition. So for superposition, first I make the distortion 0, and if I want to find out the gain, V out over V in, which is the closed loop transfer function, and you can use the same principle again, but now the closed loop transfer function is going to be A, not A1, because this is my new sort of A naught dash, let's say, the open loop gain, right? So that's the open loop gain, 1 plus beta times, again, A naught times A1. Now, if these two terms are very high, then this will again be very close to 1 over beta like before. So, which is good because that's what we want. We want this, and let's set this 1 over beta to A1, which was an intentional gain before. So we set this to 1 over A1, so that'll give us the gain we want. Okay, now let's see what's the transfer function of this VD, how much of it comes out. Now before it was all coming out, right? Because if I make V in equals to 0, V out is equal to VD in this term over here. So everything was coming out. But with this feedback, now let's calculate and see how much of that distortion comes out. So I make superposition, so I make V in equals to 0 now. So if I have to find out VD over, V out over VD, in other words, the transfer function of the distortion component, then this is going to be 1 over 1 plus A0 times A1 times beta. And you kind of intuitively see this because if I take this and redraw this, so you take this and this becomes your VD and you get output directly. So you have this element which is 1 now, and you have a feedback factor that's minus, and this feedback factor is now A naught A1 times beta, right? So basically I took this and redrew it with V in equals to 0. And this transfer function here is nothing like that, right? So V out over V in. Now if A naught times A1, that is really big, much greater than 1. So you can, and beta equals to A1, this is approximately equal to 1 over A naught, right? Because beta is equal to, we said 1 over A1, and A naught A1 times beta is much greater than 1. So if you put these two conditions, you get that. So by superposition now, if you look at your output, we said the input term here with V in, you get 1 over beta, which is A1 times V in plus VD over A naught, right? Now if you're, sorry. Now if this A naught is really large, this pretty much goes to 0, and you just end up with A1 times V in, right? So that's the other advantage of feedback, is it actually reduces your distortion in your amplifier too. Now, one obvious question is, what about this amplifier here? What happens to the distortion of that amplifier? We model this. So that's a good question and a valid question, but you can see that if this is, so let's say this is 10 times V in, right? Which means that this one here, this term over here is going to be, and we said this gain is 10, so this is just V in here. Let's say this is a large gain, then your input is V in over, let's say this was 1000, is V in over 1000 here. So it's a tiny, tiny input over here. So which means that the distortion coming out from this amplifier would be very small compared to this amplifier, right? So I broke it this way. That now this doesn't have to be two amplifiers. It can be just one amplifier, but it kind of explicitly shows you that you kind of improve distortion by just having a high gain, and usually your distortions are at the output of the stage. If it is at the input stage, you can't help it, but it's at the output of the stage. But because you have this high gain, the input you see over here, this error amplifier, is tiny. For example, here in the open loop case, you saw the total V in. So let's say you had an audio amplifier and the input was 100 millivolts. You would see the 100 millivolts straight here. But in case of the feedback, if you had a gain of 1000 here or 10,000 here, you would see only a microvolt here. So if you have only a microvolt, then your linearized model is still valid, right? And that's why we can still use those linearized models because of feedback. If it was open loop, then you'll be distorting heavily. Okay. All right. So the third thing I want to talk about, which we will be seeing a lot with feedback amplifier, is what's called gain bandwidth product. Now, so far in this this amplifier we've drawn, so we said this is A naught, this is beta. We have some V in, V out. Now, what we have assumed is that if you take this amplifier or this beta and plot it over frequency, let's take the amplifier A naught, F, it's flat, right? It's just A naught for all frequency. But that's obviously not true, right? Every amplifier has a limited bandwidth. That's just what it is in practice. So if you have a limited bandwidth, and let's say this A naught now is actually a function of your frequency, input frequency, which is always is the case. And for now, let's assume this is not. And that assumption is pretty valid for what we have been considering, because if you have a resistor divider, and let's say the input capacitor is very small, then this bandwidth is much, much higher than this one. So let's, for simplicity, we'll assume that this has a limited bandwidth, whereas beta doesn't. So if this has a limited bandwidth, this will actually start falling off, right? And let's call this, and let's say this is in decibels, so this is falling off at 20 dB per decade, and let's say this is your pole, omega naught, the 3 dB frequency, then I can write this transfer function as my old, so let me call this A naught dash now, just not to confuse with the previous DC transfer function. So that will be A naught times S over omega naught plus 1. So that's the transfer function. So if I take this now and substitute in the closed loop transfer function we were writing, then we can write that ACL as, I'll do the simplification. I'll write the expression directly, and this can be written as 1 over beta times S over omega naught A naught times beta plus 1. Okay, so if I draw the entire picture now, so this is S or F, whatever you want to write it out, or just omega. So for the open loop amplifier, this amplifier over here, you started with A naught and you rolled off, right? So this was A naught, this 3 dB frequency was omega naught. Now, this closed loop, you can see that this over here is our closed loop DC transfer function. So if we didn't have a pole, then our closed loop transfer function would be 1 over beta. So let's say usually that's much smaller than open loop transfer function. Let me just draw it in a different color to make it. So let's say that's your closed loop. Oops, sorry. That's your closed loop transfer function. And this is your closed loop transfer function. So you can see that, and this is now omega naught A naught times beta. So this is what's called bandwidth extension. So this region here is equal to or is valid when your ACL, that's your closed loop transfer function, is a lot less than open loop. Then ACL is just equals to 1 over beta. That's this region here, right? And then once you get to this region here, this asymptote over here, and go past that, so this is here, then your closed loop transfer function is usually greater than your open loop. Then the closed loop transfer function just becomes A naught. But the unity gain frequency, or the crossover frequency, the frequency at which this closed loop transfer function crosses or the open loop transfer function crosses, is actually the same for this single pole analysis, right? So essentially what you're getting is called bandwidth extension. So you started with the amp. So let's say this was 1 kilohertz. This is an omega, but I'm just writing it in frequency. Just and let's say this was 1,000, a gain of 1,000. This was a gain of 10, let's say, right? Then your closed loop bandwidth now is that same 1 kilohertz times A naught times beta. Beta is 1 over 10, so this is 100 kilohertz now. So you took a 1 kilohertz bandwidth and extended to 100 kilohertz by putting this feedback, right? So if you want higher gain now, let's say you want higher gain, then your bandwidth will start reducing. You'll get higher gain, but your bandwidth will start reducing. And if you can do lower gain, you can go lower gain and extend the bandwidth as well, right? So this is one technique we use in feedback to extend the bandwidth if you want for a given amplifier, because that's always the trade-off. Like in this one, if you decrease the bandwidth, you'll get more gain, or if you decrease the gain, you'll get more bandwidth. And that's a trade-off. These kind of, in most amplifiers, you'll find that you have to deal with this trade-off. Okay. I think that's what I wanted to cover in this slide here. Okay, so the last thing I wanted to cover is what's called the stability criteria. And the whole thing is leading to this stability analysis. Now, like as I said, before this slide, we have always been assuming that these feedbacks, like including here and everything, there is no dynamic response. In other words, these are all A naught till infinity, ACL till infinity, so on. But like as we said in this slide, they are limited bandwidth. Now, if you have a limited bandwidth and you put a feedback, you have to make sure it's stable, right? So stability means that once you put it in feedback, this ACL, you remember your control theory, after putting the feedback, all the poles of the transfer function ACL S should be in the left-hand half plane, right? Now, in typical control theory, you do this by either doing a Nyquist or a Routh criterion to find out if it is in the left-hand half plane. But in circuit, we usually use what's called a Bode plot. Now, what we do with a Bode plot is we take So like as I said, oops. So we have this amplifier with some, and what we do is we break the loop. Let's say we'll break the loop here, and we'll provide some V in here, and we'll monitor the V out here, and this V in is equal to 0. This node is equal to 0, and we don't, whatever load is here, we'll obviously connect that load, but we'll inject an input here, and we'll see the output here with all the loadings and everything, DC biases conditions met. And we'll see as we start doing amplifier design, we'll use what's called a middle book trade technique, or just breaking the loop with the loads to analyze this. Now, when you analyze this and you draw the Bode plot is nothing but a frequency transfer function. So what you do is you actually find the Bode plot for the loop gain. So you draw the Bode plot for the loop gain transfer function, and the loop gain transfer function is nothing but, in this case, A naught times beta, right? So the stability criteria is, if you take, so let's take the phase and gain. So let's say this is your gain plot, and the gain, like as you said, we start with that's your loop gain. So this will be A naught times beta, sorry, not S. So this is A naught beta, and then you roll off, right? So that's your gain magnitude. This is with respect to omega. And then for the phase, same omega. And for the phase of the same loop gain transfer function, it'll actually start with 180. I think the material I gave you starts with 0, and that's a mistake there. The reason it starts with 180 is because this is a negative feedback. It's negative here. So if you put any input over here, even before you get to the pole, this whole thing will come back inverted. And if it is inverted, that means it's out of phase. So if I give you a sine wave, and it comes off exactly inverted, that means it's 180 degrees out of phase, right? That's how 180 degrees. So for example, if you have a sine wave, and this is V in, if I just do minus V in, then that's this, right? And this is nothing but, if this was 0 degree phase, this will be 180 degrees phase, right? So that's why it should start with 180 degrees. So I think in the book, the material I gave you says 0 degree, and that's not correct. And at the first pole, it'll go through 45 degrees, 180 minus 45, and then asymptotically just settle to, not drawn to scale here, but I guess I think you get the idea. It's 90 degrees here. Okay, so for the stability, there are two things which are, and we'll talk about this in great detail. I'm just going to just mention it today, not go into a lot of detail, but what's called phase margin. Usually we just write PM, and that's the phase margin, and then gain margin. So for the closed loop amplifier to be stable, when the loop gain crosses 0 dB, or in linear gain of 1, which is called the unity gain frequency, then your phase margin is defined as this phase from 0 degrees. So like for example here, it's 90 degrees. So that's your phase margin. That means how much margin, because once it goes below 0 degree, it's unstable. So how much margin do you have from 0 degrees is basically your phase margin. So for example, if this was a 3-pole system, And let's say your phase already had fallen off below, let's say this was minus 45, this was minus, that's your phase margin. That means you don't have any phase margin. You've already become unstable, right? So in a single pole system like this, you're always stable because you cannot, your phase margin cannot go less than 90 degrees. And this is a useful technique because, like as I said, your root locus or route criteria or Nyquist plot will just tell you if it is stable or not. But it could be marginally stable. And the way we know if it is marginally stable or not is from this phase margin number. Let's say, for example, this was 12 degrees, then it is very close to being unstable. If it is 90 degrees, it's very stable. So usually we want 45 degrees plus to be what's called a critically damped system. And we'll talk more about this. Now the gain margin is the reverse. So let's say in this system, obviously the phase never goes to zero, but let's say you had a second order system or a third order system, then this phase could have gone to zero. If the phase is going to zero, at that point, that frequency you find out. So let's say the phase was falling off, like it was a third order system, the phase was falling off sharply. And let's say this is the frequency at which went to zero. You basically at that frequency, go back to your magnitude plot and find out how much gain margin you have. Now gain margin, you want it to be less than 1. So let's say in dB, this was 3 dB. That means this is unstable now. So you don't have any margin. If this was minus 3 dB, then you're stable. In other words, when the phase goes to 180 degrees, you want to make sure there is no gain left in your loop, otherwise it'll start oscillating. Or in other words, when the gain goes to zero, you want to make sure the phase has not gone to 180 degrees. So you can look either ways. So most of the time we'll look at the phase margin, because if you have, like, for example, a single pole or double pole system, you may not have the phase going to zero at all before the gain crosses the unity gain frequency. Okay. So I think I'll stop here. And like as I said, we'll be